start the lecture on advanced reaction engineering. So, in this lectures we will discuss about the trickle bed reactors. Already we have discussed on this particular reactor multi-phase flow reactors, multi-phase reactors. So, that is slurry reactors already discussed, trickle bed reactors also we have discussed. So, here today we will discuss various mass transfer correlations. That is means what are the equations are there, and using those equation or correlations how we will get the mass transfer coefficients. Okay. And then we will one numerical problems or examples that we will discuss for a particular trickle bed reaction system. So, trickle bed, what is trickle bed, that already you have discussed. So, this is a reactor. So, here catalyst would be here and gas and liquids that will pass through this bed of the catalyst, and reactions will take place at here, and from the bottoms we will get product that is come out from the reactor systems. So, here liquid, gas and solid, three components are there. Solid is the catalyst, that is the catalyst component that is present in the reactor. So, now if we want to design the trickle bed reactors, so then for a particular reactions, let us say if we want to get, let us say 60% conversions or x equal to 40% conversions for a particular reactions, then and what would be the amount of the catalyst for a particular desired conversions, either these 60%, 40% conversions if you want to achieve for a particular reactions. So, then how much quantity of the catalyst we have to put inside of the reactor, or what would be the volume of the reactors, or what would be the length or height of the reactors. So, these are the things we need to design a trickle bed reactor. So, today basically we discuss about the mass transfer coefficients. So, here you can see, so when we are talking about the trickle bed reactors, so there are two components as a reactant, that is one is the gaseous component that is as a reactant, and second one is the liquid component, that is component B, that is also a reactant for the systems. So, here case 1, that is the mass transfer of the gaseous reactant, that is limiting, or case 2, that may be mass transfer and reactions for liquid species limiting. So, there are two components, gaseous and liquid. So, which one would be the limiting component? So, that control the reactions for that particular trickle bed system. So, one first we will gaseous considering gaseous components we will discuss, and then liquid species or liquid reactant components, considering that we will discuss the mass transfer correlations or coefficients how we will get, that we will discuss. So, let us say for the mole balance equation for component A, that is reactant 1, that may be gaseous component. So, for that this is the design equations that already we have discussed in your previous class to dFA by dW equals to Ra prime equals to minus K Vg into Cag. Cag is the component concentration of A, gaseous component, and Kvg, that is the mass transfer coefficient, overall mass transfer coefficient for gas phase system. Similarly, for component B also, that is the liquid. So, for that also mole balance or design equation that we can write similarly dFB by dW equals to minus KVL into Cv. So, minus KVL, that is the mass transfer coefficient for liquid, and this is the mass transfer coefficient for gas, that is the overall mass transfer coefficient. So, if we want to design a trickle bed reactors, there is two components are there, A and B. So, then if we want to find out the how much reactants is means catalyst quantity is required for a particular conversions, then in these two design equations we can solve, and then KVG and KVL, these are the components. If you are able to know, then we can directly put for that particular reaction systems, then everything we can get. So, now question is to find out KVG and KVLs, these are the overall mass transfer coefficient. How to find out this overall mass transfer or transfer coefficient for the gaseous systems or liquid systems. So, here in the right hand side the KVG and KVL that is given. So, KVG that we can write 1 by H, and these are the components for individual steps, there are multiple steps for the component that is A, that is transferring from gas bubbles or gas phase to the interior pore of the surface of the catalyst for the reactions. So, then these are the 4 resistance are there, resistance 1, resistance 2, resistance 3 and resistance 4. Then each, if we are able to find out all these 4 components and if we are able to put, then KVG value only will get. Similarly, for KVL also, since liquid component is there, there is component B, that is means that component B, it is fill up the pore of the catalyst bed. So, here if we put the catalyst, so all liquid components will fill up that. So, that is already in contact with the surface of the catalyst. So, therefore, 2 terms means these terms and these terms, 2 resistance is not here in this case in liquid phase, only these 2 terms are there, means okay. So, these 2 terms are there and rest are not applicable for liquid phase mass transfer. Okay. So, now these are the 2 components, how we can find out. See here, if we look into the KVG, here KGAI, that is the gas phase mass transfer from gas bulk to the interface, and this is interface to the bulk interface concentration of component A to the bulk liquids, their component A concentrations, and further that resistance KLAI, and next one is the dispersions from the bulk to the surface of the catalyst, and this is inside of the pore resistance. So, individual, these are the KGAI, KLAI, KCAI, and these are the components. If you are able to find out, means what are the correlations on how to find out those correlations to get those value, then so we can substitute this, then only we can get KVG or KVL value. Okay. So, KVL, for KVL is this, and for KVL these are the components we have to find out using some correlations, and then so we can put for liquid phase or liquid components the mass transfer coefficient KVL. Okay. These are the things we will discuss. So, here why these are the things are important, KVL or KVG. So, here you can see the gaseous reactant component, component A, that is the gas and that is the limiting, let us say that is the limiting reactant. So, then if we have the material balance or mole balance equations for this, if we rearrange and integrate these equations, so then rearrange, after rearranging is this, and we know this F equals to F naught into 1 minus x A, and F A, that is the molar feed rate components A, that is the concentration or molar flow rate out from that reactor system, that is gas volumetric flow rate, and concentration of the A, that if we are able to know, then we can write this way, and this is this. So, if we differentiate this and differentiate this, then we will get this dFA equals to minus F A naught dxa and dFA equals to Vg into dCA. So, now here we can substitute this, and then in terms of concentrations we can write these equations. So, after integrating, so we will get this, or you can say this. So, and after rearranging in terms of here Ca equals to outlet concentrations of component A equals to inlet concentration of A into 1 minus x. So, this if we substitute here in this components, so in terms of the conversions, so we can write the equations, these equations, mole balance equations for component A in terms of this left hand side, that is the weight of the catalyst that is required. If we know the, let us say x equal to for 60% conversions, what would be the W or quantity or amount of the catalyst that you have to place inside of the reactor, then x equal to 0.6 we can put here. So, then Vg, that is the volumetric gas flow rate reactant component, that is known value, but KVG value that is unknown. So, that value we have to find out. If we know that, directly we can put over there, and then total amount of the catalyst for this particular systems we can easily find out. Okay. Similarly, for component B also, this is the mole balance equations. If case 2, that is their mass transfer and reactions of the liquid species limiting, in that case these design equations we have to use. And once similarly, if we rearrange and integrate these equations, Then similarly for component B or liquids we can get W equals to V L in divided by K V L ln 1 by 1 minus x B. These equations we can get. Here V L is the volumetric flow rate of the liquids. Liquid is one of the component for the reactions in the trickle bed reactor, that is liquid component. The that equations, if we know the let us say this component liquid conversions x B, that let us say 0.5 we need. So, for that how much quantity of the catalyst we have to place, and if we know the volumetric flow rates of the liquids at a particular flow rates that is passing through this catalyst bed. So, and then if we know the another term KVL, that is the mass transfer coefficient for liquid phase. So, if we know these are the components, then W, that is the amount of the catalyst necessary, that we can find out for a desired conversions. Okay. So, here this component is very important, means how we can find out KVL or KVG for component gas and liquid component. So, there are so many correlations are there. So, few correlations means the way individual resistance components, means I discussed here that KVG, these are the 4 components you have to find out, and for KVL these are the 2 components you have to find out. Only if we know for a reacting system or reaction system these are the components, we can substitute all components, and then only KVG and KVL we can find out, and that directly we can put it here in these equations or in these equations, only then we can substitute, but that is not very easy to find out that component. And also one more things, this is the trickle bed reactor. So, reactions may be different from one reactions to the another reactions, both that means reactions would be different from one reactions to reaction another reactions. Here this mass transfer coefficient Kg, Kl, Kc, that depends on the number of variables that are the type of packing. So, here the packing materials or catalyst packings, that also depends on flow rates of the liquids, gas, weighting of the particles. Weighting means suppose here's catalyst bed is there, so here's 50% means flow rate is very low, as if that all the reactant component is not weighted. So, few means free fractions, maybe 70% of the solid catalyst that is come in contact with the gas and liquids. So, then rest 30% not come in contact. So, that also we have to account when we are going to design, or we are going to calculate the to find out the actual weight or conversion or other things for the KVG, KVL value. Okay. And the geometry of the column is also very important. So, therefore, the correlations vary, correlation, this is the Kg, Kl, Kc, whatever the mass transfer coefficients we will find out from system to system, since these are the components are from one reactor to another reactors, both are not similar. These are the components from one system to another system should be different. Therefore, the overall the results or correlation that will come, that will also vary from system to systems. Okay. So, now evaluating the transport coefficient, mass transfer coefficient or transport coefficient. So, step 1 we have discussed or this type of rate equations, and this is these equations also we have derived in our previous class. In the step 2, that is liquid interface to the bulk liquids, the transfer of component A. So, these equations we have derived, and for step 3 also from bulk liquid to the surface of the catalyst. So, these equations we have derived or discussed in our previous class. So, here if we know the gas to liquid, gas to gas interface mass transfer from component A, then Kg Ai is important, here Kl Ai is important, in this particular rate Kc Ac is important. So, these are the components actually we have to find out, and then we can put in this equation to find out the rate also, if we know other components or parameters. Okay. So, now what are the correlations available to find out these are the components, means Kg Ai for this particular resistance, means transfer gas to bulk gas to the interface, gas liquid interface, the transfer of mass for component A. So, Kg and Ai. So, here few correlations here is there. So, that for step 1 means gas phase to the interface mass transfer is there. So, for that this correlations is available KGAI, that directly we can find out using these correlations. Here in the right hand side EG is there, that we have to find out. What is EG? EG in terms of feet pound force per feet cube seconds, that we have to find out, and then it we have to substitute here in the numerical value what that would come, then easily KGAI we can find out. So, how to find out EG? EG we have to find out using these correlations here, delta P L, delta P by delta L into UG. So, delta P by delta L, what is that? Delta P by delta L, that is the pressure drop per unit length of the reactor or systems, that would be given. So, here let us say this is delta P by delta L, that is given 10 to the power minus 2 psi per feet pressure per unit length. So, then this if we substitute, means if it is given for a reactor the pressure drop, then we can use that one, and UG value we have to find out. Okay. So, once we know the UG value for a systems, let us say gas flow rates, that is the 10 feet per seconds, here it is given for example. So, that UG value if it is given, pressure drop per unit length is given, 2 value we can put it here for that our system, then we will get EG. This EG if it is given in these units, then it is fine. If it is not given, or if it is given in other units EG value, then we have to convert that into feet pound force feet cube per second, that way you have to convert, and then that EG value we have to substitute here, then KGAI we can find out. So, KGAI, that is the for this. Okay. So, similarly here KGAI for this components. Okay. So, here KGI we can substitute here also to get overall transfer coefficient. Okay. One component we can find out by using those correlation. Next we will discuss about this KLAI. KLAI is that for step 2, liquid interface to the bulk of the liquids, that is their component A transferring, and for that coefficients we have to find out. So, next in step 2, liquid interface to the bulk of the liquids, there the component A that is transferring from one point to the another point. So, for that the correlations is here KLAI by DL, that is equals to this GL by mu to the power 0.441 Smith number to the power half. So, these correlations we have to use to find out KLAI. Okay. So, except KLAI, other parameters we have to know or we have to find out, then only we can substitute here to get KLAI. If it is aqueous solution, there are two cases, means when component A is the gas, component B is the liquid, that liquid may be aqueous or may be any organic solvent or organic component. If it is aqueous, then these correlations we have to use. If it is organic, then correlations B we have to use, and these correlations we have to use to find out KLAI. Let us say that is component B as a reactant, that is organic. So, then these correlations we have to use using Reynolds number, Smith number, Galileo number, that we have to use. So, then KLAI in terms of second inverse we can find out. Here DL, that is the diffusivity, means component A diffusing component B, component A is the gas and component B is the liquid. So, A is diffusing in liquids. So, this diffusivity we can find out, since there are component A and component B is there, that is in liquids. So, this DL value we have to find out for component A is going to be that diffusivity that we should know for that particular systems, that we have to substitute here. All these Reynolds number, Smith number, Galileo numbers, these are the components you have to substitute here with this. Then KLAI value we can find out, that KLAI value we can substitute here, KLAI value we can substitute here, or in the overall master KLAI value we can substitute here to get KVG, and these are the two components are left. So, these are also we will discuss. So, what are the correlations available, and that correlations we have to use to find out that particular components. So, next step 3. In the step 3 is the component A that is diffusing or transferring from, mass transfer is there from bulk liquid to the surface of the catalyst, and for that means these correlations are available we have to use. And let us say the liquid that is flowing, it has a particular Reynolds number that is maybe less than 60, then these correlations we have to use. If the Reynolds number is less than 20, then this second correlations we have to use. Okay. Here G is the Galileo number. What is Galileo number? That is dp cube rho L square into G by mu L square, and Reynolds number is GL dp by mu L. So, here G1, that is the superficial mass velocity of liquid, here L stands for liquid. So, Reynolds number of the liquids, if we want to find out superficial mass velocity of the liquids, that we have to find out, that we have to substitute here. dp is the diameter of the particles, that catalyst particles we are using, so that we have to substitute here, and mu L, that is the viscosity of the liquids. If we know that, we have to substitute here, then Reynolds number for that systems component B we can find out, and similarly Galileo number also we can find out, diameter of the particles, density of the liquid, G value is given, and for that particular systems, and viscosity of the liquids. These are the components we know. Then Galileo number, Reynolds number we can find out, and we can substitute in these equations here in step 2. Actually for step 2 these are the components are here. So, we can substitute here, means Galileo number or Reynolds number, how to find out. So, it is given here. So, these are the for step 2 actually, these components are for step 2, okay, these components, okay. And here's one more component, yeah, AI not AI. So, these are the Smith number, Reynolds number and Galileo number. So, these are the components we can find out, and we can substitute here. So, we will get it the KLAI, and here's Serud number, that Serud number is equals to, in for step 3, Serud number equal to Kc dp alpha by dl. Alpha is the fraction of the external surface of that particles or the catalyst bed is there, that is weighted. Okay. So, maybe total bed is, let us say this is the catalyst bed. So, here's liquid is coming. So, maybe up to this liquid is fill up, component B. So, these are the parts not fill up. So, these are the parts remain unweighted. So, total bed and how much percentage is unweighted, that we can find out, that is the fraction actually, okay, external surface of the catalyst or bed, that is weighted, that if you know that we have to substitute here, and diffusivity dl, that we have to find, we know for that particular gas and liquid system, and then Kc and dp. See here the Serud number we have to find out, depending upon that, means first you have to substitute REL, Reynolds number of the liquids, Smith number of the liquids. If you substitute here, then Serud number will get, that Serud number we have to put it here, okay. What are the Serud number would come, let us say this Serud number is coming, we have to substitute here, means the result numerical value, and dl value and alpha value we substitute, then from here we will get Kc in dp value, that we can find out, okay, for that system. So, here's another thing as there, here AS, that is the interfacial area of the catalyst particles per volume of the pellets, these correlations you have to use, interfacial area per unit volume, interfacial area of that per unit volume. If you want to calculate, then bed porosity plus diameter of the particles, if you know, then AI we can find out, or interfacial area per unit mass of the catalyst or pellets. If you want to note, then the density of the particles and diameter of the particles you have to put here, then AC you can find out, and EB is the bed porosity, that we have to use here to get it, okay. So, by that way we can find out Kc value. Here it is given, for example, if particle diameter let us say 0.5 centimeters and Reynolds number is 50 means less than 60, this, then this, from these correlations the Kcac value was 0.2 approximately second inverse. So, Kcac value for step 3 we can find out, and that we can substitute here, okay. Then these are the concentrations we can measure, and then rate of that particular disappearance of component A for this particular step we can find out. Similarly, that correlation Kcac value we can substitute here. So, 3 components for this overall transfer coefficient, this and this we have find out. Next is this, okay. So, these are the 3 mass transfer coefficients we have find out by using these are the correlations. So, now suppose here these correlations that is given, that we can use for to find out overall transfer coefficient, to evaluate the total resistance or maybe individual resistance, for since there are so many steps are there from transfer of or component from one phase to the another phases or from one point to the another point inside of the reactor. So, individual steps there are resistance, individual resistance if you want to find out, then these are the correlations we have to use, and depending upon that reactions, reactors, flow rate of the liquid, flow rate of the gas, diameter of particles, diameter of the reactors, or interfacial area of the particles, density of the particles, porosity, bed porosity, particle porosity. These are the components you have to know, only then so many data or means parameters we need to find a particular correlations, then individual correlations we can find out, and that we can substitute, then overall transfer coefficient we can find out to find out the rate of disappearance or component that is participating in the reactions, that we can find out. Okay. So, now here one examples that I am going to discuss. So, then means it would be very clear for you to means how means individual correlations means coefficients are there, and how that we can evaluate, and what are the means parameters or components or value is required to find a trickle bed reactors means problem. Okay. So, here let us say component A is the gas, component B is the liquid, and that is component C, that is the product, that is the liquid. So, A is the gaseous component, B is the organic liquid, and component C, that is the another organic liquid, that is as a product, that is formed. Okay. So, this is the trickle bed reactors. So, in this case reactant A and B, that would pass from the top as a co-current mode. Okay. So, that would pass through these reactors, and from the bottoms converted products and at the same time unreacted reactant that will pass and leave from the reactors. Okay. So, in this particular reactions hydrogenation reactions of organic unsaturated organic compound to convert into saturated organic. So, here the gas total pressure that is given 20 bar, and this reactions is first order reactions. Okay. Here with hydrogen, nitrogen gas also would be pass equimolar portions, hydrogens with hydrogens, nitrogen that as a carrier gas inert component, that also you have to pass with that reactants. Here mole fraction of individual component hydrogen and nitrogen is given 0.5, 0.5. Okay. And total flow rates, that is 10 mole per molar flow rate of the this gaseous component is 10 mole per second. Okay, that is given. And here dP is the diameter of the particles, spherical particles we have taken, so that is the catalyst, the diameter of that catalyst particles, that is dP is equals to 0.2 centimeter spherical particles. This is the reactor diameter, reactors it has specified diameter, the 1 meter that is given. Superficial mass velocity of the liquid, liquid is flowing, liquid mass velocity is given GL, that is equals to 5 kg per meter square per second. Okay. So, superficial mass velocity for liquids that is given, and pressure gradient that is or pressure drop per unit length inside of the beds, that was given delta P by delta L, that is equals to 25 kilopascal per meter. Okay. So, and K is the reactions rate constant at 400 Kelvin, that is given. Reactions rate constant, usually reactions we write K minus R equals to K into Ca Cb. So, here this reaction rate constant that is given for this particular reactions is 3 into 10 to the power minus 5 meter cube per kg catalyst per second at 400 Kelvin. So, this is the systems means reaction systems is given, different components for this particular reactions is given, and now we have to find out for each transport step determine its fraction of the resistance, total resistance to the mass transport and reactions. So, total percentage resistance means individual's resistance we have to find out, and then individual resistance we have to find out, and then we have to find out percentage resistance for individual resistance, total resistance, that we have to find out. And then second step is we have to calculate the weight necessary to achieve 50% conversions of hydrogens. If A is the reactant hydrogens, if we want to get the amount hydrogen that would be supplied here, out of that 50% conversion is there, percentage conversion is 55%, then that we want to achieve for this particular reaction systems or this reactions if you want to conduct in a trickle bed reactor. So, then how much amount of the catalyst we need. So, means how much catalyst we have to charge, any quantity of the catalyst we cannot charge. So, if our desired conversion is fixed, then so what would be the weight of the catalyst, means that may be 10 kg, 20 kg or 25 kg. So, that would be some value, what would be that. So, that we have to find out for conversion, say desired conversion. If we maintain these are the parameters or total pressures and mole fractions, everything is given. So, for this particular systems we next steps is to solve this particular systems. Okay. So, here additional data is given for this particular problems. Here viscosity of the liquid that is given 0.0018 kg per meter second for this particular liquid at that particular temperature, viscosity we know. Density of the liquid is also given, if we want to deal with a liquids, the density we should know. So, that is given. Diffusivity of the hydrogen in that particular liquids, DH2 liquids, that is also given, means diffusivity of component A, that is hydrogen diffusing in liquid. So, that is given, and then organic diffusivity in organic product. So, since our component B is, that is the organic liquid, that is after reactions also converted another organic products, that is also liquid. So, in that case the diffusivity is this. Molecular weight of the organic, that is reactant, that is given 168 gram per moles, molecular weight, that is the known components that we know. Then H prime, that is the solubility of the hydrogens, that is given 0.008 kilomole per meter cube per ATMs. Okay, that is the solubility of the hydrogen in that particular liquid, that is given. And then porosity of that particular pellet, catalyst particles we have taken, it has a pores. I said this is, let us say, catalyst particles, it has a pores, that porosity is 0.3. And if we take a bed of the catalyst, bed is, this catalyst would be filled up here, it has also porosity. So, that is E bed, that would be 0.4, that is given. So, bed porosity is given this, and catalyst porosity is 0.3, and catalyst pellet density that is given, that is 1500 kg per meter cube. So, catalyst property means density, diameters, these are the givens, and we are assuming that concentration of the liquids, that is component B, that concentration remain fixed or constant throughout the operations or reactions to get 55% conversions. And apart from that, there is tortuosity factor is there, and constriction factor is also given for this particular reactor, reaction system, catalyst, catalytic systems. In here catalyst is porous catalyst, it has a pore, through that pore diffusions would be there, component A and B, that would enter inside of the reactors. So, there if we want to know the inside of the pore, the diffusivity, that is the effective diffusivity, these are the component tortuosity factors and constriction factors for that particular catalyst, porous catalyst is given. So, that is known. So, if these are the additional data are given, and this is for this particular problem, some other data also are given. So, now we have to solve, means percent resistance we have to find out, conversions for this particular conversions, what would be the amount of catalyst we have to charge inside of the reactors, that is we have to proceed. Okay. So, here this is our reactions, means from the step 1 we have to start mole balance. Okay. So, this is the mole balance equations. In these equations, step 2 is the rate law, means for this particular reactions, rate law is this minus Ra prime Kv G into Cag, and component B, that is concentrations we are assuming constant, that is 1, therefore, we are not putting here, and this is first order reactions we have assumed. And then overall transfer coefficient for this particular systems we have discussed or derived this, that we have to use to find Kvg value, and then we have to substitute here. Okay. Then minus Ra primes we have to substitute here, and then that equations means individual resistance we have to find out, and then we have to substitute here, and then Kvg value will get, that Kvg value will put in the red equations, and then the red equations substitute here, then we can find out the particular desired conversions, how much amount of the catalyst we need. Okay. So, in the step 3, that is the stoichiometry that we know, means here the reactions, maybe we are considering that isothermal gas phase reactions, and for that this type of correlations is there. So, that earlier class or lectures we have discussed that concentrations at any time, that is the initial concentrations, that is the change of conversions, and this is 1 plus E x P by P naught, that is the pressure ratio for that particular systems, and here C A equals to C A naught, that same equations we can write in this form. Here Y is the ratio of the pressures for the system. Here is the fractional volume change, that is the mole fractions we know for component 1, that is the 50%, 50% A, 50% nitrogen was there, that is therefore mole fractions of component A, that was 0.5, and delta is the changes of the moles for this particular systems. This is for liquids, this is for liquid, and this is for hydrogens reactants. This is it would be this total fractional volume change, that would be minus 0.5. Okay. So, this part we know from here we can use, and the step 4 is the pressure drop. So, it is given delta P by delta L, that is the minus beta 0, that is equals to minus 25 kilopascal per meter. So, we can convert that into ATM per meter. So, kilopascal to ATM, that you can know or how to convert that. So, then it would be in terms of ATM per meters, that is the drop in the pressure inside of the reactors. Total pressure is also given, that is 10 or 20, 10 bars, I think 20 atm, 20 atm, that is the total pressure is given, that would be useful later. So, now these are the correlations also we have discussed in our previous class, when argon equations to pressure drop for a packed bed reactors we have discussed. Then alpha and beta 0, that is the pressure drop parameters, so how they are related with the cross section area, density of the catalyst, bed porosity, and total pressure. So, if we alpha beta 0 is given, beta 0 we can substitute here, and other components if we substitute, then alpha we can get, and dy by dw, that is equals to minus alpha by 2y plus 1 plus E x, E is given here, that we can substitute here. Then this equations actually is coming from here for isothermal case. So, if this part is isothermal, then we can eliminate this part, and these equations we can that would be converted this way. So, it already we have discussed in your previous class, therefore, I am not going to discuss. So, how the pressure is also changes inside of the reactors by changing of the catalyst, that parameter also will come. So, here's combining equation 2, 1, 2 and 3. Combining equation 1, 2 and 3. So, 1 is this, equation 2 is this, and equation 3 is this. So, these 3 if you substitute, then material balance or mole balance equations. See this equation, this is the concentrations in terms of the pressures, we can substitute here, this we can substitute here, and then this rate we can substitute here. Then these equations, this is the differential material balance or mole balance equations would be this. Okay. So, now if you simplify these equations, it would be like dx by dw equals to kVg into this. Here kVg is the mass transfer coefficient for gas phase, overall mass transfer coefficient. This value you have to know. Okay. So, this kVg value you have to know, and here's these parameters V0, fractional volume change, these are the known components that already you have discussed how to find out this, and V0 value that is also given for this particular system. So, then equation 5 is the ordinary differential equation that we can solve these equations, means conversions as with catalyst weight. Okay. So, this is the equations. Now, for this we need kVg value, means these are the value we have already discussed. Now, kVg value you have to find out. So, how to find out the kVg value? Already have discussed some correlations that is given. So, in our next class we will discuss the how to use those correlations, and using those correlations individual known parameters you have to put in that correlations, then kVg value we can find out, that is the overall mass transfer coefficient, and that we can substitute, then the ordinary differential equation easily we can solve. Okay. That part we will discuss in our next class. Thank you.